All right, folks, let's gradually restart. Anybody still struggling with a notebook? Not seeing a lot of hands, which is good. Not a single one, in fact. So that's good news. Either you totally gave up or you're not struggling anymore. Okay, excellent. So let's then jump into the notebooks. And the goal here is to start with, let's see where it is. Start with some basic concepts to build up towards a more complicated stuff. 45. Okay. Okay. All right. So first, we'll look at the concept of ND array, which is the fundamental building block of mxnet. And then that would, learning about ND array symbols and modules, we'll go through it quickly just to understand what it's like, and then look at convolutional networks, an example of building and training models on the NIST, well-known NIST data set with digit recognition, and we'll compare the regular kind of backprop with convolutional networks and understand convolutional networks a little bit. So looking at ND array, and again, I've seen a few hands when you raise the hands about Python. You guys, some of you know Python. If you don't, you'll learn to recognize Python code today. And we start with ND array. Can you guys in the back see this okay? Yeah? All right. So first of all, how many of you know NumPy library? I mean, if you're doing Python and some form of data science, then that should be familiar. So the good news is that ND array is your multidimensional array equivalent inside mxnet that's equivalent to NumPy's version of ND array. Now, there are a few reasons why we just didn't use the same ND array from NumPy. And primarily it has to do with ability to distribute workload to multiple contexts in terms of CPUs and GPUs, and also being able to, they call it lazy evaluation here in the notebook, but it's really about background processing where you, or asynchronous processing, where you have a matrix operation and you basically, instead of immediately waiting until it finishes execution, you put it into background for processing. The system automatically figures out how to best execute it, possibly concurrently with other steps that you've executed. And then when you really need the data, that's when you will have a block or a delay. OK. So with ND array, we have multidimensional arrays. And here's a simple example, right? So we import, this is a standard line, import the mxnet library, mx. So when you see mx, we're referring to mx objects. And we're just saying create an mx ND array out of this kind of Python list. This creates a one-dimensional array. We can create multidimensional arrays by using nesting. And then we can basically inquire about the shapes of these arrays, A shape, B shape, built-in operations that tell you the dimensions. So if I were to execute this, yes?
What is the main difference between, like, why mxnet needs this ND array? Why it cannot use NumPy array?
So that's, I kind of mentioned it briefly, but essentially there are two main reasons. Background processing. So it's able to do more than regular NumPy array. And that's why, setting things into background for background execution and working with multiple GPUs, CPUs as a computational context. But at the end of the day, you might be asking, well, you promise deep learning and all of that. Why are we looking at matrices? and the reality is that all neural networks is matrix manipulation of some form, right? We're talking about weights, we're talking about input data, and so this is a fundamental component of neural networks, and we need to start there. Anyways, so if I were to execute this, which I might have already done, so Python people out here, can you tell me what is this? It's a 3L comma, and then nothing after comma? What is that? Everything?
It's long, it's one-dimensional array.
Okay, it's everything or one-dimensional array. So basically, the syntax means it's a tuple, right? It's a Python tuple, and a tuple has usually more than one element in it. And it's just it's Python's way of indicating that that's actually a tuple as opposed to a single number in brackets and parentheses, right? Which could be interpreted as basically a number by itself. So for example, here I can extend this, and if I type a comma, oops, like that, that's actually an expression that means it's a tuple with one single element of A, and I should be able to execute that. Let's see what happens. Yeah, there you go. It kind of gives you the same output. It's a tuple with one single element. That's all it is. OK. A little bit odd looking. That's why I wanted to make sure we're all on the same page.
You can't modify it.
What, sorry?
You can't modify it, so hence the representation.
OK, yes. You cannot modify a tuple. So then, obvious, OK, so we have the shapes of these arrays, the different dimensions. One way you can initialize an ND array is basically pointing to the NumPy version of ND array, right? So mxnet ND array with the NumPy version. Here, what we're doing is we're creating a single dimensional list of numbers from 0 to 15 or to 14, I guess. So 15 elements. And then we're reshaping it to 3 rows of 5 columns. And that's, if we're going to stop here, just right. So this is the NumPy version, and then we're creating an ND array from mxnet. By default, the arrays use the float type, but we can specify D type just like with ND array from NumPy with a specific type. Again, nothing kind of super exciting here. Yeah.
Maybe talk to people, what's a notebook, how do you run, execute?
Good idea. I mean, we kind of jumped into Jupyter right away, and I haven't really explained what's going on, making assumptions here. But really, thanks, Sunil. So, what we have here are cells. And so, for instance, this is one cell. See, when I select it, it's blue. And then I can scroll up and down with these cells. And some of these cells is just plain text descriptions. Some of these cells is Python code. And I can execute each cell as dynamically. And then the context is preserved. So if I have variable b defined, it will be available in the follow-up cell. And so I can continue executing one after the other. So you can use your cursor keys to navigate around the notebook, moving up and down through cells. If you're inside the text, just hit escape, and you're back at the kind of command level, and you can scroll up and down. And then to execute a particular cell, just hit Control-Enter. But of course, they're handy buttons here at the top. And I think you know, if you haven't dealt with Jupyter Notebook before, then you can clearly see the kind of advantages of being able to experiment and then have it nicely represented in the form of a web page and then potentially even share it with your colleagues. Okay, so we were here. The numbers indicate basically sequential execution. If you run it, it turns into an asterisk to indicate that it's running, and then once it's done, it gets a number, and the output is displayed. Anyways, I think even in Anima's presentation, you've seen kind of quick shorthand notation for creating matrices filled with values. So zeros, ones, you can fill it with a particular value, or just create an empty, random kind of representation. One bit of kind of convenience is, by default, if you just print the array itself, then it doesn't display much. It just says ND array of its size, and it shows the context it's going to be executing on a CPU by default. So if you want to see the values, that's what you need to do. Add as numpy, and it will show the contents. So basic operations, they're all overridden. So element kind of wise addition, element and negation. You can apply certain functions to individual elements. There are things like transpositions of matrices .t and so on, and then finding scalar values. Again, we'll not spend too much time on this. This is interesting. You have a dot product instead of an element-wise operation. So two matrices multiplied by each other. Again, if you're rusty on matrix multiplication, you can kind of try to do it manually, right? You can imagine another matrix, a copy of this matrix sitting next to it, and then you're taking the column and row and pairwise multiply and add, and then that's going to be the element in there. Or you could just believe it that that's the right value and keep on going. Again, minor details here. Assignment basically updates the original. It's an in-place modification. So B plus A, B is modified instead of a new matrix or a new ND array is created. The slicing doesn't quite work the same as ND array in NumPy, or at least not across all dimensions. So across the top level dimension, you can select a slice. Can somebody say what this refers to? So first of all, let's look at what this A looks like. All right, so 0, 1, 2, 3, 4, 5. So if I say this, what is it going to do? 3 will be replaced by 1? Not a bad guess, but so basically, so remember that this works across the top level dimension, or the first dimension, which is here are the 3 rows, right? We have row 1, row 0, row 1, row 2. And this basically says starting from row 1 until row 2, but not inclusive of row 2. So basically just selects row 1, which is the middle row, and then replaces all the elements in that middle row by 1. So we should And then, of course, A with the colon just selects all rows, as you might correctly assume. So see the middle row, all the values were replaced by 1s. And of course, this is the same as that. Yeah. OK. Keep on going. You can slice a particular axis. But unlike ND array and NumPy, you need to use a function. And you need to specify which axis you're going to use, and so on and so forth. Some additional shape manipulations. You can reshape your matrix. Supply the desired shape. We've seen already an example of reshape, but used before. And additionally, you can concatenate multiple matrices. So here, A is the matrix of all 1s, B is a matrix of all 2s, and we concatenate them. And get that, right? Not very complicated. Anyways, I think we'll see it somewhere, so I'll just mention the broadcast as well. So when you create an array like this, it's 6 rows and 1 column. Basically, it just gives you the first numbers from 0 to 5, right, in one single column. That's all A is. And then when you say A broadcast to 6, 4, so the same number of rows, but now 4 columns, basically just copies that column and creates 3 additional columns that look exactly the same. That's all that broadcast, just kind of shifts the numbers. And you can operate like this across multiple axes as well. And here's an example of that. And again, let's not dwell too much on that part. There's example of assignment versus deep copy. Again, some basic things that you need to know when you're manipulating your matrices. And this is an interesting one, because this is, back to your question on the differences with NumPy's and the array. Now we're able to set the context and decide whether to execute on GPUs or CPUs. So in this chunk of code, we're adding the 2 matrices, and by default, these matrices are created in the same context, and then we print the result. So by default, it's CPU context, but we can change the context to GPU. Oops. And so initially, when we executed with CPU, we see CPU context, and with GPU, we see GPU. So that's where the operations will actually be executed. And if you have multiple GPUs, you can also select different GPUs. The key thing is that the operation, both elements, data elements, both matrices need to be in the same, created in the same context, so they can run either on GPU or CPU. Again, there are some examples here that kind of highlight the difference in terms of speed of execution, but let's not worry too much about this. OK, so that's ND array, really. Nothing earth-shattering here, but that's an important step for us to understand the code later on. Let's briefly look at the symbol, and then we'll try to see the convolutional networks as an example. So all of the operations that we've seen, these are, well, you could say imperative operations. You say A plus B, and they execute immediately, right? Instead, we can define a computation symbolically. It's almost like programming, right? You're writing your code, and you're saying A plus B multiplied by C and whatnot. So this is what we're doing with symbols. We're defining our computational sequence of steps, a computational diagram, if you wish. And effectively, what is a neural network? It is a computational diagram, right? You start with inputs and kind of a feed-forward fashion. You're going to perform certain manipulations, and then at the end comes out a result. And that's why we need this, because using these symbolic definitions, we're going to be able to create and effectively define our network topologies. So for an example, the simplest symbol is a variable. That's your input. And so we say, I want to create a variable called A and a variable called B. And then I can say, C is actually an addition. So we apply operation plus on the two symbols. And C is also a symbol, right? In this case, it's automatically named because plus. And now we can, at some point, invoke that symbol and run that symbol to produce a result. So a lot of the operations that we've seen with ND array have the kind of symbolic equivalent. So we've seen reshape, for example, as a function. But here, reshape is a symbol. So if we say A and B are symbols, we multiply the two inputs, we produce D. We then concurrently do a dot product. So this is an element-wise multiplication. This is an actual matrix multiplication. And then we'll take D and E, add them up. This is also a symbol. And then finally apply another symbol of reshape, specifying what kind of shape we need. And so then we can broadcast and so on. And so now we can visualize this composition of symbols. There is a nice function, plot network. And here's the symbol that we want to plot. So if I run this, I see a diagram automatically generated defining my computation visually, which is kind of very nice. But that, you can already see that it's kind of looking like a neural network. Some initial sequence, right? And you can also see that there's some parallelism that's built in. The multiplication, pairwise or element-wise multiplication can be done concurrently with a dot product with the two sets of inputs. And now we're building up to basic neural networks. We're saying that my initial layer of input is data, right? It's a variable. Then I say I will create a fully connected layer. So instead of saying I want one neuron connected to that neuron and so on, we're just saying create me a whole layer of neurons connected to this input layer, right? I'm supplying the previous layer in. I give it a name, fully connected 1, and I'm supplying the number of units I want, 128 kind of neurons. Then, on top of the fully connected layer, I'm supplying the activation layer, right? This is a kind of a function, an activation function that will be applied. And you see that net now refers to the previous layer, right? We keep reassigning the same variable. And the type of activation is ReLU, and ReLU as a linear rectifier function. I think I have kind of an example here. Oops. Yeah. So this is the ReLU function. Basically, for any inputs that are below 0, it just gives 0. And then for inputs above 0, it's just an identity, kind of a straight line. Surprisingly simple, and yet this is something that was discovered sort of not so long ago, that this leads to great results for neural networks, because a lot of other activation functions were tried. You know, kind of logistic functions, inverse tangents, tangent, and so on and so forth. And then here I'm adding another fully connected layer. Now the number of units is smaller. I'm applying another function to the ultimate output to produce my result. And again, here is the resulting neural network kind of visualized as a symbolic computation.
Can I connect the input layer with the sum of the hidden layer, like skipping previous layers, like residual neural networks?
You know, just add another input on the side here, or recurrent. Yeah. Yes, I mean, that's, in fact, hopefully time permitting, we'll see everything. Okay, look, I want to show a convolutional layer as well. There's a bit of a factory that allows you to create convolutions, but you get the gist of it, right? Like with this, you can create complex structures. This is, in fact, the inception factory that creates the inception neural network. And you can see how, oops. How complicated that is. So you can construct neural networks symbolically this way, and that's the kind of profit here. Okay, look, one quick remark about a module. With the module, you're able to essentially train your neural networks. So here is a definition of a network. And then I can create a module out of it. And then run predictions. So you see I could just invoke a function like fit and pass in the iterators for the training set, supply the batch size, additional parameters, and it just keeps on going. So it's a hardness for you to exercise your symbolic network and train. It's a convenience kind of thing, and then you can run things like predictions. And so let's go back to the MNIST data set, or not go back, actually see an example of a handwritten character recognition, a digit recognition data set. So if you guys are able to follow, you can try executing. So from the main outline here, right? This is the MNIST tutorial that I'm talking about here. You can open that link. And first, we need to load the data. And the data is actually stored in Jan LeCun's server. Now, in the past, we had issues when multiple people in the room were trying to download that data set. And so in case you're having issues, here's an alternative link that you can try. But hopefully, it just works from the source that you have. This server is not really intended for kind of mass downloading. OK, so all this is producing the training images. It downloads the training digits, and it knows their labels. And then also it uses these are the validation, they call it, but it's really the testing data set. And these are the important kind of outputs, train underscore image, val underscore image, and so on. And so just to see what it looks like, you can actually execute the next cell. And again, it's not really too relevant to our topic, but you can see you use matplotlib and pyplot, and you can generate nice plots of bitmaps. And these are the data that we have. Note how we just looked at the first 10 bitmaps from the train underscore image data set. and they have the appropriate labels, the known labels that we're trying to predict. If this data set, just for you to see what it looks like, right, we could basically say train shape, right? So we have 60,000 images, and each image is 28 by 28 pixels. Each pixel is a grayscale value from 0 to 255 of that point on that image. And okay, moving right along. What we need to create are iterators for training and testing, and this is the whole purpose of the next cell. So we're doing a bit of magic here in terms of reshaping that input data set. We're actually turning it into a float, so remember that each pixel is a grayscale value from 0 to 255. We're dividing that by 255 to produce a float value between 0 and 1. And we're also defining batch sizes, and this is in batch sizes of 100 that we're going to present that data to the neural network through this iterator. Okay. So the first thing that we attempt here is to use the standard, your traditional multi-layer perceptron. Old school stuff, basic back propagation with just fully connected layers. Again, skip the kind of math here. You could see that the resulting network, see, we're creating the input layer, then we flatten it, so we turn every single pixel of an image, 28 by 28, into one single input, right? Then we're fully connecting this via 128 hidden units. Again, there's a lot of black magic going on here, right? Somebody decided it's 128 units. Well, you can experiment and change that. The activation layer is added, then another fully connected layer, and now with 64 units. So finally, having another activation layer and a fully connected layer to finish off with 10 units. So why is it that we have 10? Right, 10 digits we want to predict. So each unit is going to output a value, and our prediction is going to be the digit with largest value output by the unit. And again, so here we're basically creating a visualization. Nothing earth-shattering, but the reason we have the 1 here is because it's 1 bit. It's 1 bit deep, and it's a single image that comes into the neural network. So now we're able to train this, and now we're exercising some built-in functions like feed forward. So on that model that we've created earlier, where is that? Oh, well, we're creating a model right here, sorry. I don't know why I'm looking here when I can look straight in front of me. But I'm specifying the learning rate, the number of epochs through which the training data is going to be cycled, and I'm also able to supply a callback function when I try to fit the data. The idea is that the system will report progress as it's going along from batch to batch, and you can see the results, right? Did I actually run this? Yeah, you could see the progress. Well, I mean, it's a feed-forward, very simple network. And it's not running on a GPU. It's just CPU. But I think we're done, right?
Yeah.
So validation accuracy or testing accuracy, 97%. Okay, cool. So what can we do with this? Just for fun, so over the training data set, we actually get 98%. Some of these steps you may not see. I've added a couple of steps, but these are just simple additions to what you've got. And this is kind of normal that over the training data, we have a somewhat higher accuracy. Though, of course, we want to avoid overfitting. And a kind of exciting bit here. Note that we're, so we're using the same iterators, so validation iterator, train iterator, to kind of run the model over it and produce the accuracy results. But with a bit of Jupyter magic, with embedded HTML, we can do fun things like this next cell, where effectively we get a built-in JavaScript form where we can draw a digit, right? So I could try to see if I draw 2, whether it will actually recognize it as such, right? Okay, this one is doing okay. Let's see, 3. Okay. How about 5? See? It's not so good. What about 1? This shows as 0. So, but recall that in all the training sets and all the training images, all the writings were perfectly centered kind of thing, or at least they were more or less around the center. And so that's what the neural network was trained on. So if you try to draw things somewhere on the side, you know, it's not familiar with what's going on. It's not seeing it. It hasn't seen this before. But also, this is still a basic backpropagation, so its accuracy is not so good. And we can actually see which digits were misclassified in in that training data set.
Can we see the activation of the hidden layer somehow?
You mean, how do you mean? Like, what are the values that were done during activation?
Yeah, do we have access to the hidden layers?
Anima?
Not directly.
Yeah.
Not directly at this point, but there is some sort of that you can actually get the. You're looking for the output activation.
Yes, for hidden layers.
Yeah, so it's not possible in an easy way, but I can point you.
So it's possible, but not in.
Yeah, not with the API.
Ah, okay.
So, okay, going back to the next cell, so we can actually plot digits that were misclassified. Again, this section you may not actually have in your notebook. This is just some quick addition that I've done, but it's actually interesting to see, well, what are the digits that the system missed? The 97% accuracy. But we can see that especially difficult digits are things like this 5. Well, to us it looks like 5 probably, but you can also see how the system could have had trouble. 9, 6, 9, okay, they're fairly normal to recognize, but this 4 is a little weird too. I assume it's a 4, right? But all of these were misclassified, and this gives us kind of the indices in the data set that were misclassified. And so the next step is for us to try to do build a better network with convolutions. And I think here is where the recent advances in deep learning really shine, right, with these instruments like the convolutional layers that are specifically designed for images. So remember that with our initial backpropagation network, all the pixels were flattened, right? It's just 28 times 28, whatever is the number, right? We can actually see what the number is right here. Oh, maybe not. Yeah, well, 784. These pixels are completely independent. We're not taking advantage of any relationship between them in space. And the idea behind convolution is that pixels that are next to each other probably are related, and that information, that carry that information that we need to preserve. And the idea behind the convolutional layer is that we're going to take a bunch of neighboring pixels and apply a certain function to them and collapse them effectively to a single point. So take a bit of a field of a bunch of neighboring pixels and collapse them into a single point, and hopefully gathering all the information about related pixels together into one single number. And one way to do this is, and this is the receptive field, right? So imagine that these are my pixels. What we've done, well, I guess I'm walking away from the microphone, but we've added here a pad of zeros around. And we're taking a receptive field of, I guess, 3 by 3 here. This is the kernel size, 3 by 3. And we're moving it along, sorry. Yeah, we're moving it along the image. Our original input image here is actually 5 by 5 here, right? With a pad around it. So with a 3 by 3 receptive field, how many of these can we have in a row and vertically and horizontally? If we take, for example, this receptive field, what we're going to do is apply a kernel matrix by performing a multiplication or inner product between the actual pixels and that kernel. And the resulting value we're going to record in the new output. So that's the process of collapsing. Now, the interesting bit about the convolution is that you may have, obviously you start out by not knowing what are the values of that kernel and how we're going to multiply it. These are the things that are learned in the process. And the other thing, these are effectively the parameters of that convolutional layer that we're trying to learn. And the other thing is, we may be applying to the same image multiple kernels, creating multiple different versions, multiple different filters, if you wish. And so from a single image, we may actually generate multiple images by applying different kernel matrices in this convolution. So that's the whole idea. And then to complement this, we're also using a concept of pooling as an additional layer. So not only we're collapsing related pixels together, but the intuition here is that maybe these are neighboring pixels, right, shown in yellow. And we're going to try to find, in this case, a pixel with maximum value. So this is a common approach, right, 7. And replace these 4 pixels with a single pixel with the maximum value 7. The intuition is this. Imagine that one of these, well, they might not be pixel. It's a data point now in that image filter. But that pixel represents a dog, right, that we've recognized, or a neural network recognized. So 7 means I've recognized a dog face, and then this kind of maybe also looks like a dog, but less so, and so on. And so by applying this 2 by 2 pooling, we're now collapsing that information. We're saying it doesn't really matter where the dog appears. Maybe it's in this top left corner, or maybe it's a little bit further away. But we'll still recognize that there's a dog somewhere around there, right? And that's the intuition behind having this pooling approach. We're trying to compensate for different translations there. And there's a notion of stride. So if we're walking, the pool is 2 by 2, and we're walking by 2 elements across that matrix. OK, so we're quickly wrapping up. We're now creating a different kind of network with all these layers. So let me execute that. See, first we apply a convolutional layer. Our kernel is 5 by 5. And we're using 20 different filters. So we're going to learn 20 different filters of 5 by 5. We'll then apply an activation function, the tangent function. We'll then apply a pooling layer of 2 by 2 with the stride 2 by 2 that was shown actually in the picture. Then we'll use another convolution, now with a larger number of filters. But because we've done pooling and convolution, our dimensionality decreased somewhat. And then another activation, another pooling. Finally, we'll flatten the results, fully connect them, apply another activation, another hidden layer, another fully connected layer, and then finally get the results. And this is how this network looks like. And if we look at the dimensionality, so,
Question?
yep, please.
Just out of curiosity, when I was looking at this first one here, is there a specific reason you've chosen those activation functions as they are and not like random ones?
So this is, again, this is the black magic and the art of doing this, right? Some of these networks are well-known networks that have been published, and you just take them off the shelf and apply as is. And otherwise, you take this one and replace the tangent by something else, and you may discover some brilliant stuff. But I mean, yes, there are some. There's some intelligence behind them, but oftentimes it's still fairly empirical, right? OK, but with a convolution, if we have 28 by 28 pixel image, our kernel size is 5 by 5, right? We didn't actually use any padding. And therefore, how many of these kernel or receptive fields are going to be in one single image? How many are going to fit? We're shifting by 1, right? By 1 pixel. So 5 by 5, shift by pixel, shift by pixel. What are we going to get? So 28 minus 5 minus 1, right? 5 minus 1 is 4, so 28 minus 4, we're going to get 24. So basically, we're reducing the image dimensionality from 28 by 28, it's now 24 by 24 pixels. But because we have 20 different filters, now it's not just a single bit, right? We have 20 different different versions of that image, if you wish, right, with different filters applied. And we're going to be learning the weights for this. And then a pooling size likewise affects dimensionality. You see now with a pool of 2 by 2, from 24 we get to 12 by 12. And then eventually another convolution, reduce dimensionality, and ultimately we end up with just 500 different signals. Remember, we had 784 originally, but here we've actually added multiple filters. So the data has been originally enriched with different filters, and then we get to 500. One bit I wanted to mention, but OK, all right. So this is it. And we can now train that function. One thing to observe here is now we're changing in the feed-forward model definition. We're saying use the GPU context instead of CPU. So now we're doing training on a GPU. And that will result in a speed up. You can actually try and switch to a CPU and compare the results in terms of speed. Is it still going, or are we done? It's still going. But you see the accuracy there is already 98%, 98.8, 99, like almost 99%. With the back prop, we had 97%, right? So we've managed to increase the overall accuracy. Is it done? Yeah. And, well, you can kind of see it here. 98.9 over training data, even higher. And the kind of interesting test, we can now take one of the digits that was misclassified by the backprop and see if this system managed to classify it, right? Because I just used the first one or some misclassified digit from the misclassifieds list. Again, this is a slight modification of what you have in your notebook. Oops. Okay, so I need to rerun the misclassifieds. This one. No. You know what? Let's not worry about it. Yeah, let's not debug it. And I think let's stop here. The point of this was that the function was able to classify one of the digits. You actually saw it in my previous execution. I may need to change something here to get it working. Anyways, that's NIST dataset with convolutional neural networks. Question?
Yeah, and how many optimizers implemented in MXnet? Are they the same functionality as, let's say, Keras, or Keras has more implemented?
Yeah.
Let's say Keras has like Adagra, Adadel, Aramas Pro. What about them?
You have all of these. Yeah, you have all of these. Yeah, we can implement, we've actually got regular optimizer metrics, all of those.
So the same principle, the same functionality.
Yes.
Okay. All right. We have Sunil next, or Cyrus next? Okay. Perfect. Thank you very much, guys.
So I'm seemingly hooked up. I'll try to be quick, given that I have a flight. Name is Cyrus. I'm principal SA with AWS AI. We saw convolutional neural networks that are very good at basically dealing with the spatial association between fields. Next, we're going to talk to things that are good at picking up sequences, things like language. A little bit of theory, and towards the end, we'll take a look at the code, and I refer to the place that the actual notebook is. So try to see the sentence. The Spanish king officially did something that abdicated shouldn't be here, but the Spanish king officially, try to imagine that's triple dots in something of his something Felipe. Felipe will be confirmed tomorrow as the new Spanish something. So there are a bunch of clues here that we can actually fill out those dots. There is the knowledge, the prior knowledge that comes from whatever knowledge graph that you have previously. You know the language, you know if there is something his, and then there is something king, and there is some sort of application. There is likely to be son, because there is a prior knowledge of the Spanish system being a hereditary rule. Besides, there is some basically sequential information like the linguistic cue that you know when you see his, the next thing you're going to see is son. So using the sequential information, you can actually understand a sentence. You can predict the next word based on the context that is prior to that point and based on some knowledge graph that you have learned previously. So it comes in different flavors. These are called recurrent neural networks because it's like any dynamical system, the state of each, basically, you have different times. So at every time step, the state is related to the state that you had previously. So at t-1, you have something. At state t, you would have an association with that. So that means that as you build the sentence go forward, word by word by word, as you go forward, based on the statistics you have collected, you can predict the next word. So the current state of your network, based on the number of the sentences that you have, affects what you're going to predict. You can do a bunch of stuff with it. You can label an image. You can caption an image. Actually, different words that you can extract from the image vector that you give it. You can do sentiment analysis, that you give it a bunch of vectors, and it comes out and it says, happy. You can do machine translation, which a sequence relies on another sequence, basically depends on another sequence. You're trying to do, for instance, translating from English to Spanish. So what you're going to have is, basically a vector of words going in, a vector of words coming out. You can do video labeling, which is that thing, but you have multiple inputs. So you see that when you have a sequence and you want to understand the sequence, you want to make predictions based on the sequence, then you're using the recurrent neural networks that each state has dependency on the previous state. So let's get down to a little bit of background. Today we have heard from almost everybody talking here about the notion of computational graph. A computational graph is a graphical presentation of a computational operation. Here, simple. X, y, multiply becomes z. Here, you calculate y from x multiplied by w, the same w to the power of 2, sum, and then multiplied by lambda. So you can actually represent an operation, a computational operation, based on a graph. That would be a recurrent neural network. And you start doing something called unrolling it through time. So when you're trying to expand your operation, as you feed forward and backward, if you remember one of the pictures that Anima had when she was doing this optimization of the memory, that were the blue dots and there were the gray with the blue frame, and then going and coming from the other side up. So when you go, that's a pass forward and a pass backward. As you go through, you're calculating your gradient, basically you're calculating your loss, you're predicting an output, and then you go backwards and then forwards, backwards, forwards until you're done. So here you do that through time because every step you go, you have dependency of the previous step. So at t-1, the data is important to make a prediction as point t. Same thing as language. The king of Spain this morning, something, something in favor of his son. The word you predict with high probability is abdicates because you get his son, you get the monarch, you get the favor. So the combination of those things gives you basically through time, you unroll the basically computational state as you move forward. So this is good. It's got a huge problem. Most of the networks we've seen so far, you give it a fixed length input, it gives you a fixed length output. The cases of convolutional network, if you give it the exact same thing, it gives you the exact same prediction each time. It ignores context. So we need to introduce context, and we should be able to deal with different sizes of inputs and outputs. If we can do that, we have something on our hand that is potentially capable of dealing with natural language processing. Other than that, we pretty much cannot. So here is one specific architecture of recursive neural networks that you give it an array of n, length n, it spits out a summarization, a single output. So these are your inputs. These are your hidden states. This is your output. This is your observed value. And this is your loss function. So it goes through the entire network and has everything, computes it, and spits out a single output. It summarizes it. Second type that is important for us is a 1-to-m, that you give it something like image captioning, right? You give it some array, and then you give it some matrix or whatever, and as a fixed size, and it's going to summarize it through training and going up and going up and going up, but finally basically at some point coming with a y of tau. So now, if we combine the two, we have solved the problem of n-to-m. And that was a very excellent paper coming out as encoder, decoder, or sequence to sequence that you can implement using LSTM, not recurrent neural networks, in order to make basically having a basically predicting an array, predicting a vector, sorry, based on an input vector, and those vectors would have different sizes. So this is very good, works in theory. For decades, it eludes researchers to do any sort of training in there. Because of something, I give you just a Google search term. If you don't know it, figure it out. It's called the vanishing gradients. The problem happens as the good thing is it relies on the previous network as it's going to calculate the loss function and the gradient, and it multiplies it by itself, by itself, by itself. It either explodes the gradients or it makes them diminish, depending on the values being. OK, I stop here. So, and then we do have LSTM networks. The thing that happens is, as we are training network forward and backwards, what we're losing is sometimes we contribute basically a cell becomes involved in a calculation that it shouldn't have been involved, and it starts losing its value. So we want to protect that value. We want to get that value when we want it. We want to go back 5, 6, 7 steps before 7 words ago in the sentence in order to understand that. Is there anyone German in this group? Right, so you do basically stack your verbs at the end of the sentence, right? So it's, for instance, Germans really love to stack their verbs at the end of the sentence, especially when they have modals. Sometimes you have 3 verbs at the very end of the sentence, and in between a bunch of things that have no relation with one another, structural relation, right? So with that kind of stuff, then you want to go have this long-term dependencies. You want to go backwards several levels, and you want to preserve those values, and you want to pick those values out when you need them, when you want to use them. And that is the motivation behind LSTM. It says, I give a mini network instead of a cell for every LSTM cell that I have. This, by the way, is from the picture. I should have put the caption. Actually, I have references at the end. This picture has been taken from it's not Bishop. It's from the Goodfellows MIT Press Deep Network. So also, these ones are my interpretation of what he's done. So far, every picture you see is from Goodfellow. So what you have in here, you go, I give an internal structure to my cell to be able to protect it, to be able to go backwards, to be able to see only if when I'm permitted to extract this value, to pop its value, diminish it, destroy it, or to insert a new value. So as you see, this is called the gated system. So there are a bunch of neural networks, RNNs, that are gated, LSTM being one. So you have an input gate. This is one cell. You have an input gate. They usually have an activation function that is a sigmoid function, something that produces a real value between the 0 and 1. So you can, different levels of activation you can have. Then the other thing you do, you create a self loop that sometimes it could be linear. And through that linearity, it deals with diminishing, doesn't matter. So, and then when you go backward through propagation, every time you have to see basically the output gate, if it provides you with value 1, the value inside the cell, inside the inner state, would be used for computation. If this thing says 0, it just stays there. Same goes here. When you're updating values, basically updating weights on the way backwards, if the input gate is actually giving you 0, you're not touching that value. That means when you can go all the way backwards without diminishing the values, without diminishing your gradient, and you can actually refer to your history. So that's pretty much an LSTM network looks like in the more abstract vision. So that hidden layer, some or all of them, according to Graves, you can actually do all. There is no necessity for having some. So you can actually have this layer replacing the normal hidden layers with LSTM gated cells. So let's see how it goes. Here what you're going to see, this is from Graves. Here there's going to be some digits written, basically the handwriting is going to be here. And here is when it discovers it, and it resets the network when it discovers something. We're looking for something called delayed inference. Delayed inference is, I don't really know what it is. I want to go backwards, a couple of steps back, and oh, that's an L. I know what you have written. Just take a look at that. That E had to wait a very long time. Same with H. This A. F was good, actually. This A had to wait. So as you see that, every time you see that happens, I made a prediction, I reset the network, and I'm good to go. So that delayed inference is, because I have the previous state, I can work backwards in time, and I just figure out what it's, basically use the information I had in the past in order to predict something about the future. I read it in his paper, what he was talking about is something about predicting, I really don't know. I think he had in paper, it's got a couple of things. One was about how much you press your paper on the press your pen on the paper or something. There's some extra indicator. I don't remember what was in the paper, but it's publicly available to see that. Then, this is the short version of an LSTM network. Now we're going to take a look a little bit at the code. Any questions so far? I'm usually an excellent speaker. Nobody has questions when I talk. So here's how we build that. That seems very ominous. Gates and open and close and all of, it's no longer that you have like these activation functions in layer by layer. You've got several activation functions, pay gates, pay note per, so that's a really hard thing to code. Luckily, you can give it a bunch of basically, how many LSTM layers do you want? Forget about embedding for a moment. How many hidden units that you want? And then from an LSTM.py, you go do unroll. So unroll is unrolling the computational graph. That's why it's called unroll. So you go unroll, give it the number of layers. Sequence length is coming from something called the bucketing, basically the bucketing API. So we set that language gets actually put in a big matrix, right? And the different sentences have different length. So when you have something that you get your maximum length for a sentence, or let's say for a sentence, for basically your vectors, you end up with a lot of empty spaces that is going to eat up your memory. So what you do in bucketing, you're going to cluster the basically vectors based on in separate basically classes of length, up to 10, up to 20, between 10 and 20, within 30 and 40. But this is not something you want to worry about it at this point, because here with the example we're going to see today, the maximum 129 would do. For the tweets you sent me, 256 would do. That was weird because tweets are 140 character. 200, you need a 250 for maximum length. So here we unroll stuff. We give it how many layers. We give it something vocabulary that we see in a bit how it's been created. Hidden, embedded. So we built that thing. We give it the input file. And we go do something called mini batching. That means we don't want to train the whole network. We want to train it in small batches. And then train the network basically based on bucket sentence iterator. And give it the sequence length, that was the bucket size. We give it the vocabulary that we have produced. We'll take a look at vocabulary in a minute. And we're good to go. And do a feed forward, as we did before. On a GPU, we give it how many epochs. So every epoch is forward and backward. So the example we see, it took about 75 to reach where it needs to be. It's learning rate. You give it some number. Anyone knows what a learning rate is? Pardon me? Yeah, how much you go forward each time you want to learn something, especially when you're dealing with a stochastic gradient, some sort of basically steep gradient base. So momentum is 0. Does anybody know what a momentum is? Yeah, it's kind of a speed. So you know, when you drop a ball in basically downhill, it might get stuck at a local minima, but it has to have some sort of speed to jump off from the other side and continue if the other side is going to be lower. You know, we have multiples of valleys. So there is no momentum here. Forget about Javier. And then you say fit, and that would start epochs of training the model. Now I'm going to switch to the notebook. So this is char level. This is basically character level language model. You would be amazed how much you can understand from sequence of characters, from frequency of characters. For instance, you can create things that sound like a specific language. You know, if you give a bunch of words in a language, there are patterns, like in English language, like when you have T-I-O-N, when you have O-U-V, like OUs, like color or flavor. That's a joke on my American friends. So, and me, we do this. We do in between, actually. So, and then you can actually, based on that statistics, you can produce words. Now, better even, if you give speeches of a certain person that has a certain consistency in the way he talks and is not very randomly shooting things, then you can even create words that are appearing next to one another that actually resemble that person's speech. It's not that you're always creating English words, but every word you produce has an English sound, even though it's not a word. So here is our data. The data set here is Obama's speeches. So this is a data set of Obama's speeches. We turn them into a vocabulary by turning them to vocabulary, breaking them into constituent letters. And then we're not even using one of an array here. So far, we haven't done anything very strangely mxnet here, right? We're just creating this. So that's basically a term frequency for your vocabulary. So in the term frequency, we know the letter G has appeared 41 times within the vocabularies are 83. That includes a bunch of stuff. You usually have to clean it up, but W has basically appeared 10 times. Now we create the LSTM model. So that was our vocabulary that it kept appearing previously as we saw that on the slide deck. Now we're creating the LSTM model with 3 layers, 512 hidden units, LSTM hidden units. We order it to be created and filled up from a file. Done. This is the training that we saw. Here I did run the training. It took a little while to produce it. So the inference part, I'm not getting to statistics. I'm just going to run this thing, right? So here, the only thing that's happening in here, something important here. Let's see, that's had some Obama here, Obama. So here, this is one of the good things about mxnet. You can actually No, that's a callback. Checkpoint, yeah. So you can actually, at the end of every epoch, you can record the result, the parameters of your model. And when the models start diverging, you can actually stop it and use what you have done. So what you have in here in the code, I have only one epoch. In one epoch, you can't get any much training. It produces barely a word when you want a sequence. And here, and it takes a long time. It takes about half a day, 3/4 of a day to do that. We're loading, cheating a little bit. We're using a pre-trained model. Basically, that's epoch 75 after 75 runs. And we make inferences. Here, we're trying to create a sequence with the length of 600 that should kind of look like an Obama speech that begins with the United States of America. That's what it's come up with. And it gets at some point ready to go, ready to go, ready to go, because there's not enough data. So let's try something else to see if it can work. Hello. Uh-huh. Very often you need to be connected to your server to make it work. So don't restart. Let's see if we can produce things. No kernel. I run it all, kernel, restart, and run all. I restart the whole thing. It doesn't take much. And you do that. So when you go to your server, there's mxnet notebooks. There was Python, that you saw that already. There were outline. And that was Carolistium. Let's try to make a few changes in your network. For instance, you can go and change your back size in order to see if it helps. Change your training rate to something smaller or larger. The problem is we play with it, but at the end of the day, we will have to load it from the one that is pre-trained. So I saved this thing. Or maybe it doesn't like this one. Let's say hope. Oh, the kernel's busy. That's why. So the kernel's busy calculating something at the moment. Would you like to open that and try to change a few things? OK. With that, I'm running to the airport. One question. Somebody sent me tweets from a very famous person between 2009 and 2017. I did 75 epochs on a single GPU, and it took me about more than a day. Single GPU, but it just, we know that you throw more hardware, and then it starts basically performing better. Yeah. Hope is not the first time in the world, and the consequences would be, this is all extracted from nothing but statistics on the number of characters in a bunch of above speeches. Not words, not grammar, not n-grams, or not, none of that, none of that. It's basically a term frequency matrix of characters within a speech. Ready to go, ready to go, ready to go. He's seemingly always ready to go. So I'm done before I get fired.
I won't take much time. I know we are coming to an end. Probably take less than 5 minutes, and we'll kind of summarize. I thought it'd be great to show you guys a couple of quick demos and notebooks, something that might be useful. One's called fine-tuning. So the process of fine-tuning is essentially taking a pre-trained network, and you take the benefit of what the model has learned and apply it to a problem. So very practical, and a lot of people use that. So the process, essentially in this case, we will use an ImageNet trained model. So we'll download a ResNet model. And then what we will do is we will essentially take the last fully connected layer. So ImageNet model, it's a 1,000 layer. It's got 1,000 categories. So in this use case, we'll just train a model to differentiate between a cat or a dog. So what we do is we will replace the last layer. We'll replace the last layer with a simpler layer, in this case with just 2 categories. So the number of classes is 2, because we'll do a binary classification. We'll call this helper method, get fine-tuned model, and it replaces that layer. And then we'll run the training process. And it will learn the features. So as long as you have an extensive data set, you will be able to fine-tune this image model to classify, say, cars or not cars. In the Silicon Valley show, they had hot dog or not, if you're familiar with that HBO show. So similarly, you could do that. And here's an example. So we will take this image. And let's see. So this is a model of a dog, and here we can see that it's classified this with a probability of 99.9%. And then there's some code here to inspect, while training, to see. Typically we want to see what happened when we trained, why wasn't something classified or not classified. And some of the inputs, you can see that's really hard to say if it's a cat. Like as a human, we could probably interpret, but also sometimes in your data set, when things are sparse, it takes a while for your network to recognize. Sometimes adding more conv layers or other parameters, you might get better results. But this is at a high level, showing how fine-tuning is possible. Here's a link to the data set and the code and the setup. So if you guys want to copy, you should be able to get this going. I have 4 more minutes, 3 more minutes now. So I'll just do quickly. I'll show a demo of object detection. So there's a process, one of the models called fast RCNN. R stands for regional region. CNN, of course, we went through convolutional neural networks. In this case, the entire network, it actually, we kind of split the last layers. So we used to have a single fully connected layer, but we split it and have 2 different outputs. One is a softmax, which tells us the classification, just like in the MNIST case, we had a classification for different digits. In this case, we'll have for different categories, which will be, say, aeroplane, humans, and so on. And we'll have a bounding box regressor, which is actually trying to find the object and where in the image the object is. So short, what the layer looks like is we essentially cut the network somewhere in between, and we will retrain the network. So we'll take, in this example, we'll take a VGG network, which is an ImageNet winner of 2015, I believe. And what we'll do is we will run the entire image, rather than the pooled image, through the convolution layer. And then we have something called as region proposals. So what we are doing is, since there's spatial preservation between, say, in the conv layer and the activation, so we know that, let's say we take the top left pixel, in the projected image, we will still have that there. So we'll use that intuition and build the object detector. And that's what the network does. This is a whole code that kind of sets up the network, make this available. We'll use the Pascal Walk 2007 data set, which has 20 different labels. What I've done is just to show how fast we can do some of these things. We can run this through an example. My machine's all the way in Oregon, so we will see some delay here. Yeah. Meanwhile, I can take questions on actually any of the topics, so needn't be restricted.
Distributed mxnet, how it works? Does it find weights for one batch and not mistake the average, or like how it trained the model?
So if you think about the averaging generally happens on a mini or your batching level on each of the GPUs. So if you're talking about data parallelism, we can, things are happening at a multi-GPU level, and we have a hierarchy, essentially a hierarchical model to store the parameters, so they get pooled and averaged at that point.
Make the average of weights, right?
Correct, yeah. So in this case, it's identified it as a motorbike with 97.3% accuracy and put a bounding box. We can even extend this. So let's, for example, we can, I can take a live webcam image and send it to the model. So in this case, the model is being transferred all the way. The image is being transferred all the way, and you can see it's detected. Put two different bounding boxes where it thinks, because there's region recommendations, so it can tell you which region and with what in what box the person appears. But this is a great technique, and it's not quite real time, fast, and there's a next iteration which is faster RCNN. But if you're looking for more real-time video and stuff, there are other models like SSD with single-shot detector and YOLO. You look only once. Those are good state-of-the-art models. But fast RCNN is a great model for batch prediction for object, and you can extend, as I demonstrated, not to just 20 labels, but use larger data sets to get object detection with mxnet. It's kind of what I had in mind to show. Again, I can stay back. I know we are at the end here. We'll stay back, happy to answer questions one-on-one and guide you in the right way. So thanks, guys. Thanks for your time. Bye.